Hi. Today we are going to talk about our last topic of the semester, simple harmonic motion. This topic applies to different scenarios, such as a spring and mass system or a swinging pendulum, anything that oscillates regularly, returning to its starting position in a regular motion without any friction is considered simple harmonic motion. Once you add friction, it can still be simple harmonic motion, but if there's enough friction, it might stop being simple harmonic motion. It may not oscillate at all. So I'm going to start by just discussing the math. And in this particular lecture, the math is a little bit advanced, so I can't give the full details because it's a little bit beyond the level of this course, but I can give some results, and then we can explore the results and try to understand them. We're going to begin by thinking of the spring and mass system as a horizontal arrangement, but it turns out that if it's vertical and just hanging in the air, all of what we are going to learn is still valid. It's just a little easier to talk about it horizontally because we don't have to worry about gravity. So here's an illustration of a spring with a spring constant K, and it is starting at an equilibrium position, which we would call that x equals 0. Now, if we compress the spring a little bit, so I'll draw that with a blue compressed spring, and same, if we do that, we may have some, x initial, some starting position. And if we let go, but the mass is attached to the spring, well, then what's going to happen is it's going to start moving to the right. It will get to the equilibrium position. That's when technically the net force would be 0. And it will overshoot to the same distance on the other side. And then it will go back and forth, back and forth, back and forth. In fact, if we were to graph the position x versus time, it might start at some negative x value, to the left being negative, and then it's going to just oscillate back and forth. Essentially, it will keep going forever if there's no friction. If we try to understand the forces acting on that mass, let's do it again without all of that stuff. So there is going to be, in the blue position, there's going to be the force from the spring and the normal force and the force of gravity. Normal force and force of gravity are just kind of canceling each other out. So it's only the force from the spring that really matters. When we're in the red position, the force from the spring has changed directions. And again, the normal force and the force of gravity are going to cancel out. So really the only force we have to pay attention to is the spring force. So if we were to say net force equals ma, the net force is given by Hooke's law. That's my spring force equals ma, and we get negative kx equals ma. And if we rearrange that, we get a equals negative k over m times x. So here's where we don't really have the math available to solve this equation, because the acceleration is related to the velocity, which is related to the position. So in a way, the math here is a little bit circular because we have acceleration, which again, it's related to the rate of change of velocity, which is related to the rate of change of the position. We have that sort of rate of change of the rate of change being related to the position. And this is a little bit tricky to analyze. But if we do analyze it, what we find out is that the frequency of the oscillation is equal to 1 over 2 pi times the square root of the spring constant over the mass. So frequency is how many times per second it oscillates. So that is, a high frequency is very fast, and a low frequency is very slow. We also can define the period as 1 over the frequency. So the period would be 2 pi times the square root of m over k. So what's the trend? If the spring constant is high, that means it's a very strong spring. The frequency will be high. It will go really fast. It will go back and forth really fast. On the other hand, if the mass is large, then the frequency will be small. So if we take a spring and we put a heavy mass on it, it's not going to move very quickly because the mass is very heavy and the spring really isn't strong enough to make the mass move very quickly. So I'm going to illustrate this with a simulation. Okay, so here we have a couple of springs. We can change how big the spring constant is, making it a fat, thick, robust spring, or a very skinny, light spring, or we can keep it just at the default value. And when I place a mass, it stretches the spring out a little bit away from the equilibrium position or from the natural length. We can, in fact, show the natural length here, and we can show, let's go to the introductory. We can show the natural length and the new equilibrium position. So even though this is vertical, because the spring stretches out, it just creates a new equilibrium position, effectively canceling the gravitational force acting on the mass. And so this oscillates the same way the sideways spring and mass system oscillates. And if I displace it a little bit and let it go, it's going to oscillate back and forth, back and forth. Now, we can put a little reference line here so I can bring it down to just touch that. We can pause the motion and play the motion, but if I watch this, it's going to keep going back to my reference point, essentially forever, because there's no friction included yet in this simulation. If we want to include friction, let's put in our equilibrium position for the mass. This was the natural length, and I'll put in a reference line so we can see what happens. So let's put the middle of the mass on the reference line. And then I'm just going to let it go. Now there's a little bit of friction here. This damping represents friction, and we can see the amplitude, the oscillation gets smaller and smaller and smaller. Eventually, this will stop, or at least the oscillations become so small that we can no longer see them. So that's what happens with friction. As you can see, this first mass I got going, it's still going. So let's see what happens if we change the mass and make it a bigger mass. So again, small mass. Has one equilibrium position, that's this green line terminating at the end of the spring, or if I put a new mass, I get, oops, if I put a new mass, I get a new equilibrium position. And an even larger mass, we get a new equilibrium position. So let's see what happens when we increase the spring constant. Okay, when I increase the spring constant, we've got an oscillation. It's 1, 2, 3, 4, like that. If I reduce the spring constant, it's 1, 2, 3, 4. So we can see that as the spring constant got smaller, the frequency also got smaller. Small frequency means it's moving slowly. Large frequency means it's moving quickly. Let's see what happens when we change the mass back to a smaller mass. 1, 2, 3, 4. So even though I have a small spring constant, the frequency is increased. And if I put a high spring constant, this thing really moves fast. Okay, again, with that small mass, we're getting a much faster oscillation. That's exactly the trend that we were talking about. What about if I change gravity? We can see as I change the force of gravity, the location of the equilibrium position changes, but the speed, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, or even no gravity, 1, 2, 3, 4. As far as I can tell, the speed isn't really changing, the frequency isn't really changing as we change gravity, and that's to be expected because our formula for the frequency did not include gravity in any way. So the spring and mass system is not the only system that obeys this type of relationship and has this kind of sinusoidal motion. Another example is a simple pendulum. So for a simple pendulum, we just have a mass on the end of a string with a length L. If we look at the forces acting on this mass, we really just have tension and the force of gravity. So we can do a net torque equation. Net torque equals I times alpha, where the torque we pick as our pivot point, this point, because it's actually pivoting about that beginning of the string. And so the tension itself produces no torque because it points right toward the pivot point. The only torque is produced by the force of gravity. So we have the torque G equals moment of inertia for a point mass is just mr squared, where r is the distance between the point mass and the pivot. That's just L. So the moment of inertia turns out to be ml squared. And then we have alpha. What's the formula for the torque? Well, we're going to have the, it's going to be a clockwise, so it's going to get a minus sign, minus the force of gravity times the radius, which is L, times the sine of theta. Now, remember, when we go to rotational variables, the theta is kind of like our delta x variable. It's our displacement, but it's an angular displacement. And the alpha is kind of like our a variable. So to get an analogy with the formula for the spring and mass, we want to solve for the acceleration-like variable. We can cancel one factor of L, and if we write down force of gravity as m times g, we can see that the m's also cancel. And our alpha is minus g over L times the sine of theta. Now remember, let's write it again, alpha equals minus g over L times the sine of theta. So the alpha is like the A, and the theta is like the X. So this equation looks similar. A equals a negative constant times X. This is my A variable being a negative constant times the sine of my X variable. So it's actually not really very similar. However, if the angle is small, you can use what's known as the small angle approximation that says the sine of theta is approximately equal to theta. This is true for small angles when you're doing radians. You can check that out in your calculator if you don't believe me. In fact, anything under about 15 degrees will give less than 1% error if you make this approximation. So with that approximation, we have the acceleration is approximately equal to minus g over L times theta. So this really looks a lot like the formula for the spring and mass system. The difference is instead of a K and an M, we have a G and an L. So if we look at our frequency formula, that was 1 over 2 pi times the square root of K over M. We might expect there to be a frequency formula. Instead of having K over M, which appears in my equation, we might expect it to be 1 over 2 pi times the square root of G over L. So this would suggest that unlike the spring and mass system, changing the gravity will change the frequency of a pendulum. If we increase the G, increase the gravity, the frequency will go up, that the pendulum will swing faster. If we decrease the G, it's going to swing slower. The formula also suggests that the mass doesn't matter for the pendulum. So for the pendulum, the mass doesn't matter. If I change the mass at the end of the string, the frequency shouldn't change. Whereas we saw that it did change with the spring and mass system. And finally, there's no spring constant, but instead of a spring constant, we have a length of the string. And this indicates that the longer the string is, the lower the frequency, and therefore the slower the motion will be. Whereas if the length is very small, we should get a big frequency. So let's check that out with a different simulation. So we have a pendulum here. I can pull it back a certain angle and let it swing. Now, what happens if I change the gravity? If I turn the gravity up, it swings faster. If I turn the gravity down, it swings slower. Okay. Oh, I gave it no gravity, so it was just going to keep going forever with no gravity. Okay, so what happens if I change the mass? Let's stop this. Let's leave it pause. Let's put in some high gravity so that it's swinging quickly, kind of a 1, 2, 3, 4. Or if I want to count complete oscillations, we start on one side, it's 1, 2. Actually, we start 0, 1, 2, 3, 4, 5, and so on. Now, what happens when I change the mass? A lot of mass, 0, 1, 2, 3, 4, 5. Very little mass, 0, 1, 2, 3, 4, 5. So at least for these small angles, This seems to approximately have the right dependence. It doesn't depend on mass. The bigger G is, the faster it moves. Let's check the length. We said with the big length, it would slow down. Hard to tell there. What if the length is small? 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So it does seem to follow this formula. Okay, if we wanted to, we can put a stopwatch out, and to time it, let's stop this thing, and we can pause and press play on our timer, but because it's paused, nothing's happening. So if I want to get an accurate reading on the period, I could let this thing go one time, but there's going to be a little bit of error in when I stopped it. Okay, I get 1.44 here. So to do better than that, we can reset the timer, start it over, and we can count 10 oscillations. Then any error I have in when I stop is sort of reduced by a factor of 10. Let's try it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 13.4. That's for 10 oscillations. So the period would be just 1.34. If that's correct, and I think it's much closer, I was off by almost 10% when I did just a single oscillation. So for that reason, when we're measuring for the spring and mass or the simple pendulum, when we're measuring the period, we want to count 10 or 20 oscillations and then divide that number by the number of oscillations to get the period. And we'll get much more accurate results in that way. And let's just take a look what happens when we add some friction. Well, hard to tell, but it looks to me like the oscillation's getting smaller. Let's up the friction so that we can see this effect magnified. So it keeps oscillating, but the size of the oscillation, the amplitude of the oscillation gets smaller. Okay, so that is just a quick introduction to simple harmonic motion. We don't have any homework problems on simple harmonic motion, but we do have a lab on it. So you can use these demonstrations and examples to help you get a sense of how the labs work. Now, I wanted to spend a little bit of time just talking about the final exam and how to prepare for it. So as I said in announcements already, there will be 12 problems on the final exam. You will have 2.5 hours to complete it. So from 11 until 1:30, and then from 1:30 to 1:45, you have, or from whenever you complete the exam to 15 minutes later, you have that 15-minute window to take your page images and upload them. So it's a little bit longer than a regular contest, but not much. There will be 12 problems and you choose 10. 4 of the problems are going to relate to the last chapter on thermodynamics. So that's heat engines, finding the work output for a cycle, the heat input, the efficiency, those types of things. And then there will also be some problems on waves. So that will be waves in strings or waves in open or closed pipes. There will not be any problems on the simple harmonic motion. That is really just to give you a little bit of background information so that you can do the lab. But there will be no test content on of that on the final exam. The other 8 problems will be drawn from the rest of the material from the semester. So that's not a lot of problems to cover everything we've learned. And so what that means is you really need to focus on the big picture items, things we spend a lot of time on. You might expect to see one projectile motion problem and one problem that has to do with net forces and finding accelerations and tensions and things. Maybe I'll give you a problem for net force that uses a pulley, but where you have to include the mass of the pulley, so there's a little bit of torque on that rotation of the pulley. We've done problems like that, and that kind of kills 2 birds with 1 stone, and that's the type of problem that I like to do on a final so that I can test, multiple areas without giving you something that you've never seen before. All of the problems on the final should be similar to problems you've done before in homework or on exams. So what you need to do is practice solving problems. Do not watch my videos anymore. Just don't do it. Don't just look at the exams or look at homework. Don't flip through your notes and try to read through all the homework problems you did and memorize them all. That will not work. But what you should do is go back, pick some problems that seem representative, like something we did a lot of in the lecture, something that you saw on the exams, and try to do those problems. You don't have to do a lot. Do 1 or 2 projectile problems and then move on. Do 1 or 2 or 3 force problems. Forces, we had pulleys and we had inclined planes and we had tensions, and there's multiple couple chapters on forces, and so there's a few different types of problems to do. Look for the big things. Lastly, you should really start at the beginning of the semester and work your way forward, because you have very limited time. You don't have a lot of time to prepare for the final. So if you start, once you're done with the material on this last unit, you start at the beginning of the semester and work your way forward, supposing you only get halfway through, the exams, trying some problems here and there, or through the homework, trying some problems here and there, at least the ones that you didn't get to are the ones that are only a couple of weeks in the past. So always start at the beginning, work your way forward, because, things happen, you run out of time. And if you run out of time and you didn't get to study the last unit or 2, well, that's pretty fresh. The only exception to that is if you skipped an exam, missed an exam, or if you had really bad exam, but the other exams were good, you might want to spend more time focusing on that content, because either if you miss the exam, you never really got it, or if you didn't do so well, maybe you did the work, but you didn't really, everything didn't click at the time. But if you go back now, you may find yourself having a better time with that material. So put a little extra time in there for an exam that you missed, or an exam that's significantly worse than your other exams. But that's it. That's what you need to do to prepare for the final. Labs are, I'm continuing to grade the new labs coming in, but also any regrades this week. So you can continue to make corrections up until Friday at the start of the exam, but that is the absolute hard deadline. I cannot accept anything past that, because I have to grade everything and submit your grades this weekend. So at that point, there won't be time to make any more corrections. So if you're unsure about how to make corrections on any labs, contact me, meet me in Teams, or let me know if it's not clear what you need to do. Okay. Thank you for, if you're still watching this, thank you for watching all of these lectures. I know it's hard, it's boring to watch video after video after video. So I really appreciate your time and attention, and good luck on the final. Thanks a lot.